nice street button.
Okay, so Wilkinson made a very important contribution. Now you might ask yourself, so what's the big deal? Why use rhodium, which is very expensive, to do something you can do with nickel, rainy nickel? And the answer to that is because homogeneous catalysts, of course, have the possibility of steering selectivities. And one of the important things in hydrogenation reactions is very often if you start off with a so-called prochiral alkene, one that in one step can be converted to something that has chirality, that you might need to, for whatever reason, steer it in a certain stereochemical direction. But before we get to that, I just want to mention one further thing on the Vasquez compound, and that is that what has also been studied is that you can, of course, vary the phosphine, right? And in this study here, look at this data here, kinetic data. If we take triphenylphosphine, we have a relative reactivity of 41. If we decorate the phosphine, the phenyl ring of the phosphine in the full position, so in the para position, with chloride, it goes down to 1.7. And if we decorate it in the full position with a methyl group, it shoots up to 86. And if we decorate it in the full position with a methoxy group, it shoots up to 100. So what we're doing, what are we doing? We're doing alkene hydrogenation with derivatives of the classic Wilkinson's catalyst by using different phosphines. And we have a different, we can steer the rates, we can increase and decrease the rates. So what we're doing is we're using different phosphines by varying the substituent in the full position. Now that's very interesting data. Can someone rationalize that? Yes, very good. The first step in the reaction is ligand dissociation. So if we have a stronger sigma donor ligand, this ligand dissociation step is going to occur faster. Very good. Now what if I were to tell you that it's been shown that the rate determining step in in Wilkinson's hydrogenation is the H2 oxidative addition? So yes, that's important. That's certainly going to be an effect, but the rate determining step is H2 oxidative addition. Sort of changes things a bit. So this step is the one that determines the rate. Now let's go back to the data. The reasoning is the same, right, as Julia just said. Clearly, if we increase the electron, the sigma donor strength, if you will, of the phosphine, what do we observe? An increase in the rate. Now why is that? The reason why that is, let's go back to Vasquez. Remember with Vasquez compound, we said that hydrogen activation, or oxidative addition of hydrogen, occurs in a concerted fashion. And it proceeds via a sigma dihydrogen complex. Remember that? This intermediate here. Now, what is that sigma dihydrogen compound? Let's look at the interaction that's going on there in terms of orbitals. Well, you can see it at the bottom here, actually. Here we have the sigma dihydrogen compound. The hydrogen-hydrogen sigma bond interacts in a sigma fashion with an appropriate d orbital of sigma symmetry. But what do we have? We've got sigma star orbitals also that act as pi acceptors from the metal. So this is a sigma dihydrogen compound. It's an intermediate on the way to a formal oxidative addition. Right, so we've got, let's just draw that. So this is the sigma orbital, and these are the sigma star orbitals. And here is the metal, for example. This might be, for example, let's say a dz squared orbital. and this would be an orbital of pi symmetry, a d orbital. So we have a sigma donation and a pi acceptor. Now, that is the orbital interaction in a sigma dihydrogen compound. In fact, this is an intermediate which cannot be isolated in many cases. It was a purported intermediate in hydrogen activation reactions or hydrogen oxidative addition reactions. And in 1983, a guy called Gregory Cubas, actually isolated and characterized a sigma dihydrogen complex and proved that, you know, it's an intermediate in these oxidative addition reactions. Now I'm digressing, but there is experimental evidence that these things actually exist and they can even be isolated, and he just did that for tungsten and molybdenum from the Department of Useless Information. Now, this interaction here clearly suggests that the hydrogen-hydrogen bond strength is going to be weakened, because you have a sigma donation that's going to weaken the strength of the sigma bonding interaction, and you have a pi back bond to anti-bonding orbitals, which is also going to weaken the HH bond strength. Now, if this pi back bond is very strong from the metal to the anti-bonding sigma star orbitals, that's going to result in the hydrogen-hydrogen bond in the H2 molecule getting weaker, and we're going to move faster to reductive elimination. If the pi back bond is weak, in other words, if the metal is electron poor, then that formal oxidative addition is going to occur at a slower rate, isn't it? So that's the key to understanding why we have this trend here, isn't it? Because as we increase the electron donor strength of the phosphine to the metal, we increase the electron richness at the rhodium center, and that results in an increased back donation to the sigma star orbital in the H2, which leads to a faster rate of H2 activation or oxidative addition, which is the rate determining step in this reaction. So you can clearly see beautifully illustrated here, a methyl group is a sigma donor. It pushes sigma density into the phenyl ring here, and ultimately into the lone pair of the phosphine, resulting in the metal becoming more electron rich and facilitating an increased pi back bonding to the sigma star orbital of the H2. So you can very easily rationalize this if you understand what the H2 is doing and how it's interacting with the rhodium. And Vasca's compound is a beautiful example that we can use to understand that.
There was a similar thing in the last lecture, no? Where you have the increased electron richness, which then weakens the back bonding.
Yes, yes. Well, I think you're thinking about when we were discussing hydroformylation. Or?
Yes, I think so.
Yes, yes, using similar arguments. That was what you're thinking about, I think, is when we were discussing the Tolman electronic parameter.
Yeah.
Remember, where you have an increased the pi back bonding in that case to a CO, which then affects the CO bond strength, because you're populating the sigma star, the pi star orbital in that case. This is a sigma star orbital, but it's of pi symmetry. And that then results in a weakening of the CO bond, which is reflected in the CO stretching vibration in the infrared spectrum. So, that's a little bit about this very important compound, and this is just a cycle again. Very well investigated catalyst cycle, and H2 is oxidative addition is the rate determining step. But indeed, what you said, Julia, also might play a role, because, of course, the first step is phosphine dissociation. So, but they found that all things being equal, it depends on, the overall rate depends on H2 addition. Now, again, let's come back to what I said a moment ago. So what's the big deal? We can do hydrogenation with much cheaper systems. Why would we want to spend time and money using rhodium? And it's because we might want to do an asymmetric hydrogenation. If we start off with a system that has a CC double bond, or even a CO double bond, that when hydrogenated is going to generate a chiral center, we might want to do it in a way that we have stereoselectivity towards one and not the other enantiomer. Okay? And again, another Nobel Prize. These three guys, Knowles, Noyori, and Sharpless, were awarded the 2001 Nobel Prize for exactly addressing that issue, and for their work on chirally catalyzed hydrogenation reactions. Okay, so basically, this is a very important. They made a very important contribution. Sharpless sort of did something a little bit different, the so-called Sharpless resolution or Sharpless epoxidation. We're not going to discuss that today. But Knowles and Noyori were sort of the guys that really put asymmetric hydrogenation onto the map. Okay? And again, this just illustrates, these are some silly examples you've probably seen from intro organic chemistry courses. Why is this important? It's important because of biological function. We know this business of two enantiomers having different properties in terms of how they interact with receptors. A classic example is spearmint and caraway seeds. They essentially, the compounds responsible for the smell are mirror images of each other, enantiomers, with different stereochemical configuration at the chiral centers. Spearmint, of course, tastes refreshing, and caraway is what you would add to make stews and stuff like that, right? Totally different smell, because it interacts differently with your receptors. And you can imagine actually starting, if you want to make this, you can start off with a compound that has a CC double bond, let's say, installed in that position there, the precursor. And if you hydrogenate that without any stereo control, you're going to end up with a racemic mixture. But if you want to do the hydrogenation in a way that you only get the R or the S, you're going to have to somehow do it in an asymmetric way. And you cannot do that with heterogeneous systems, really. I mean, the Lindlock had this, you end up with a cis stereochemistry, but it's difficult to control the stereochemistry using heterogeneous systems. So we have to use homogeneous systems if we want to do stuff in an asymmetric fashion. Another example, which I think is a little bit more dramatic, is if we look at these two compounds here, this is an agent that is used for treating arthritis, naproxen. Its mirror image isomer, however, causes liver poisoning. Right, so you've got to get this right in pharmaceutical chemistry, otherwise you're liable to cause serious damage. Another very good example of this is so-called thalidomide. In the 1960s, women were taking this drug for morning sickness, and the results were disastrous. I mean, there were children born heavily deformed because they did not get the right stereoisomer. So this is very dramatic, and we've got to get it right. Now, what are we actually talking about here? We're talking about starting with an achiral substrate, or a so-called prochiral substrate. Let's write that word down. Prochiral. All right. Something that's prochiral is a substrate, per definition, that in one synthetic step can be converted to something that exhibits chirality. Now, a classic example of that is this ketone that I've represented here on the left. That ketone is decorated with an H and an R group, right? It's prochiral because if I were to imagine, for example, hydrogenating that CO double bond, I would end up with the chiral center at the carbon because there would be four different, well, okay, let's say there's an H there, so it wouldn't be chiral. Let's say if I were to brominate it, or install some group here that would end up with the chiral center, then it would be chiral. Well, actually, this isn't the best example in terms of hydrogenation, but let's suppose I have instead of an H, another R group there, which is different, R prime. Then if I were to do the hydrogenation, it would end up being chiral, right? Because I'd end up with a chiral center. Now, what's happening energetically is we end up with an achiral substrate, and there's two possibilities. Now, if you have stereo control, what you're actually doing, it's a kinetic issue. You're basically lowering the activation energy. You're lowering the activation energy towards one of the stereoisomers which then drives selectivity in that direction. That's energetically what's happening in a stereo-controlled reaction. Now, to understand how this works, we distinguish, and we had this a couple of weeks ago when we were looking at alkene polymerization, and this was briefly mentioned. I'd like to revisit that. In terms of alkenes and in terms of ketones, prochiral substrates, we talk about a so-called Re and a Psi phase. What are those? Prochiral ketones and alkenes. How do we determine what is the Re and what is the Psi phase? How we do it is the same way as we determine absolute stereochemistry in organic chemistry, using the Kahn-Ingold-Prelog nomenclature. You assign priority, so let's do that. Let's take this flat as a pancake ketone here, which is in principle prochiral, and let's assign priorities. What has the highest priority? Oxygen. What is the second highest priority? R group. And the third hydrogen. So it's 1, 2, 3. It's clockwise. It's clockwise. So if I view this ketone from the top, I have a clockwise orientation, and that face I call the Re phase. In organic chemistry, it's the same, right? If you're assigning absolute stereochemistry, remember you'd call that R for a tetravalent carbon atom. So it's very simple. And the bottom face is the Psi face. So if I flip that guy around, it's going to be the other way around. Okay. Now, the first example in the 1960s by Knowles, demonstrating the possibility of doing asymmetric hydrogenation, was the hydrogenation of this prochiral alkene using a rhodium catalyst to make hydrotropic acid in 15% enantiomeric excess. Now that's useless in a way, but it at least demonstrated that you can skew the stereo control in a certain direction. And the ligand he used was this chiral phosphine, right? So you see it's decorated with 3 different groups. When that guy's coordinated to a rhodium center, the phosphorus atom is going to be chiral. And because it's chiral, it's going to induce chirality in the way that the hydrogenation takes place. So when the prochiral alkene approaches the rhodium system bearing this chiral ligand, it's going to steer it in a certain direction, yielding, according to this energy diagram here, a skewed distribution in the enantiomers. And we talk about enantiomeric excess, right? So he managed to do that and demonstrate that, which was a very important stepping stone in realizing the dream of doing asymmetric hydrogenation reactions. Now again, let's get this right. How do we assign Re and Psi phases? Here is an example of a prochiral alkene. We're looking at it from the top, right? If we consider this alkene here, for example, okay? Well, actually, that alkene is different because there's 2 different carbon atoms here. But if we consider this alkene here, we've got a CH, we've got a CH2, and we've got a group here. Actually, this isn't a good example because we've got 2 CHs here. But that group is going to have a higher priority because it's CH2. Here we've just got a CH.
There's just count the H.
You-
The C is the contradiction of what's connected.
Exactly. But strictly speaking, this would have a higher priority because there's 2 H's attached to it.
It's just an H next to it.
Yeah, you look at the one
H, CH.
carbon atom at a time, right?
You have an H, CH2, and a C connected to other.
You've got, that will have the highest priority. That will, all right, let's make things simpler. All right, this is a bad example. Let's pretend we have a methyl group here, okay? Let's do it like that. So if we have a methyl group there, that's a bad example. So let's pretend that here we have a CH3 group. Okay. Now I think it's clearer. What would be the priority? Well, this would have the highest priority, that would have the second highest priority, and that would have the priority 3. Do you agree with that? Because here we've got, this carbon is attached to a carbon attached to a carbon. This is attached to a carbon but then a hydrogen, and this is attached to 2 hydrogens.
But isn't the fact that you have a double bond, like, shouldn't you account for that as well? That the carbon is bound, it's double bond to another carbon. I don't
It's
remember
like
exactly.
CC instead of
Yeah.
C. You can't do it twice.
Yeah, I thought
All right,
so too.
all right, all right.
It's still the same.
Yeah, but
So it will be 1, 2, 3.
Wouldn't it be?
All right, let's let's do this. Let's put a tertiary butyl.
Okay.
Okay, I just want to demonstrate how you would count this. So that's now CH. That's CC, CCC, CCCC. So this is definitely going to have a higher priority. This will definitely have the second highest priority, and that from the point of view of this from this carbon atom here. So that would then be 1, 2, 3. So that's clockwise. So this would be the re phase, and the bottom would be the C phase. Okay. So that's how we determine. So sometimes it's difficult. Okay. If it's not so clear, but yeah, that's I think a illustrative example. Now, let's get back to this business of asymmetric hydrogenation. Now the thing is, Knowles now demonstrated in the late 60s it's possible to do this. And from that time, there's been a whole plethora of asymmetric phosphines that have been made that when coordinated to a rhodium system will impart, for better or worse, some sort of stereo control in the hydrogenation reaction. And these are some classic examples, right? And they've got funny names: tadol, binat, binol, diol, box, dufos. I don't expect you to memorize structures of these phosphines, but these phosphines are used to do asymmetric hydrogenation reactions. The first example where this was employed very successfully was the synthesis of an amino acid called L-DOPA. This was done and employed, in fact, by Monsanto, the same company that did the Monsanto acetic acid process, remember, that we learned about some weeks ago. In the 1970s, this was work done by Knowles. He was working there, and he came up with a way of converting this prochiral, see, maybe that's an even better example there. It's easier to assign the absolute rotation. Converting that selectively to this intermediate B, and then doing a deprotection to get L-DOPA. Now, L-DOPA is an amino acid. That's important. It's an intermediate or a precursor in the synthesis of dopamine in the brain. And L-DOPA, of course, has another stereoisomer. We have a chiral center there. And only the L form is biologically active. It is used in the treatment of Parkinson's disease. And this was the first example where a commercially successful product, pharmaceutical product, was synthesized using an asymmetric catalyst. The catalyst that he employed was a rhodium-1 species, cyclooxydiene dipamp. Dipamp is this ligand here that he used, and it has an RR configuration. So the phosphines, in both cases, have RR configured. They're chiral. Because remember, they're going to be coordinated to a metal, so they're going to have, as with tetravalent carbon, 4 different groups, and you can assign stereochemistry using the classical Kahn-Engel-Prelog nomenclature or rules. So it happens to have an RR configuration, and the complex itself was actually rhodium-1. Let's draw the complex, because there's the formula, but I'll just represent it for you. So it's rhodium. I use a star to indicate that the phosphine is asymmetric or chiral. And cyclooxydiene, let me just think how I'm going to draw this. I'm going to draw it the other way around. So That's the complex. That's the catalyst precursor. Cyclooxide-IE is a group that's used in synthetic inorganic chemistry. It's a great group because it's a good leaving group. It's a diolefin. And it coordinates, it roughly looks like that, to a metal. The counter ion is BF4. It doesn't really play a role. You can use whatever you like. But if you take this guy and you do hydrogenation, you get excellent stereo control and a high selectivity towards this amino acid, which is used in the treatment of Parkinson's disease. And the important thing here that some people forget is not all chiral phosphines are going to do the job, right? It quite often employs trial and error. But the important thing is to design it in such a way that that stereochemical information is useful in predicting how the substrate is actually going to approach the catalyst center and bind to it. Here I have a model of this complex that he made. All right, that's the rhodium center. And if you look at the X-ray structure of this guy, so I've taken away the cyclooxide-IE, right? Because what happens in the first step is that the cyclooxide-IE decoordinates, and then the substrate attaches here and the chemistry takes place. But you can see that these rings are conformationally locked in this configuration, right? And because they're conformationally locked, because we have these groups here, right? These O-me groups here, these methoxy groups are conformationally locked, okay? And that's why you will see now how this actually works in a moment. But if Knowles, for example, didn't have the insight to understand how you can sort of transfer stereochemistry to prochiral substrates, and yet put the methyl group in the para position here, it probably wouldn't have worked, right, as effectively. Because this methoxy group not only induces chirality, but it also prevents the free rotation of these rings. And you will see the free rotation of these rings. Okay, this is actually, sorry, this is not correct. That's better. Okay, so you see these are flat, and these are sticking out. Look at that. If these methoxy groups, and it stays conformationally locked. Now, excuse me, these carbon atoms should be flat. They're benzene rings, but I ran out of sp2 hybridized carbons. But it's conformationally locked, and you'll see now how this works. Okay, so we use a chiral phosphine and a synthesis of L-DOPA. And L-DOPA has a very interesting story, actually, because it was picked up by a British neurologist in the early 1970s, who went to a conference where he saw someone presenting the synthesis of L-DOPA, and the fact that Monsanto had commissioned the synthesis of it, and he had patients that suffered from this disorder here, encephalitis lethargica, which basically rendered them completely catatonic, right? They didn't respond to anything at all. And he started giving them L-DOPA, and actually they recovered completely from this illness. Unfortunately, and a movie has even been made about this, which is really worth watching, with Robbie Williams, he found that they needed an ever-increasing dose of this L-DOPA. And eventually, he had to stop giving it to them because the dosage was too high, and they went back into this catatonic state. So L-DOPA seems to have a very powerful effect on neurological processes, right? And it's not just using the treatments of dopamine, but you can actually get patients suffering from this actually to recover. All right, so there we have it again, very important process, early 1970s. The mechanism of the reaction is slightly different to what we have with, what we just saw with Wilkinson hydrogenation, where we have phosphine dissociation and then hydrogen activation, oxidative addition of hydrogen. What happens in the case of these systems is that we generate something like this in situ, and that is generated, of course, by cyclooxide-IE basically decoordinating from the rhodium. The active species is rhodium while it's cationic, and S represents here the solvent molecules that just basically occupy these vacant coordination sites, okay? And what happens then is you basically have the precursor, so if you want to make L-DOPA or an amino acid, you start off with something called an enamide, which is basically bears CC double bond and a ketone. This is a simple model of a type of an enamide, which is a precursor to an amino acid, and it's prochiral. And this is basically what happens. It coordinates not only via the CC double bond, but also via the ketone. That's an important point in how we managed to induce the stereochemistry. Then you get cis H2 activation. Remember, it's concerted. And now's the key point. Depending on how that prochiral alkene approached and coordinated to this chiral catalyst will dictate what the absolute stereochemistry is of the product, okay? Which is chiral, it has a chiral set. And the way to rationalize this, which is what Knowles has done, is to say, okay, let's look at the model. Let's look at the model of the catalyst. There it is. Now this is the X-ray structure of the catalyst precursor, right? The rings are conformationally locked. Now let's consider, now in his paper I've turned this ketone upside down, sorry, this alkene, because for some reason he swapped it around. But, all right, we have the Re and the C phase. Remember, if we count priorities of that prochiral enamide there, that you will see that the top face is the psi phase, because you have an anti-clockwise configuration. Look at this. There's a CC double bond. Here we have an N that will have top priority, then a COOH second priority, and then a CH2 third priority. So the top face of that prochiral alkene, because you have an anti-clockwise orientation of priorities, is psi, and the bottom face, if you flip it around, would be Re, psi and Re. So the alkene can, in principle, approach the chiral catalyst in two ways. It can approach from the Re phase, and it can approach from the psi phase, can't it? Are there other possibilities? Let's think very carefully about this. I've built exactly this alkene that is represented there, okay? Here it is. Here's the CC double bond, all right? Here's the COOH group, and here is the NH with a ketone. There it is. Now, as I've represented it here, the top face is the psi phase, because first priority, second priority, third priority, anti-clockwise, psi. If I flip it around, first priority, second priority, third priority, clockwise, Re and psi, okay? Now, there are two ways that this prochiral system can approach this catalyst. It can approach it in the following way. Remember, the ketone also has lone pairs on it, so those are going to coordinate as well. Here is our chiral system with conformationally locked rings. That's important, because look at this. If this guy wants to now approach, remember the CC double bond is going to coordinate, and the ketone is also going to coordinate. So let me just try and get this right. So it can coordinate like this. Look at that. See, it forms a square planar intermediate. It can coordinate from this face. Do you see that? CC double bond here, oxygen bond here. The oxygen's coordinating, and the CC double bond is coordinating. It can approach like this, but it can also approach the other direction. Okay, let's try and get this right. So from the other face, just need to adjust this. It can approach like this, the other way around. Now, here's a key point. What about it? Why can't it approach like this? Would that be a different structure? No. Why not? Because this guy has C2 symmetry. So, this is C2 symmetry, which means whether this approaches like this or like this, you're going to end up with the same structure, because there's a C2 symmetry axis. Now, have I convinced you that there's two ways that this prochiral system can approach this? All right, now the question is it going to approach from the Re or the Psi face? And what Knowles has done, which I think is extremely instructive, is to say, well, let's have a look at the steric demand at the catalyst center. These phenyl rings are sticking out, and those are sort of no consequence. So if a substrate approaches this rhodium center, the bigger groups are going to get out of the way of those two things blocking it over there. And he's drawn a so-called quadrant diagram to figure this out. So this is the quadrant diagram for this RR dipant catalyst, which was used in the synthesis of L-DOPA. Okay? And what you get, it doesn't just work for L-DOPA, but if you start off with a prochiral enamide, you always end up with S configuration in the amino acid that's formed following the hydrogenation, or L. You know, remember you have these two different notations, S and R, and L and D. L is S. And why is that so? Because here, let's have a look at our model. Okay? So here is the CC double bond, and here is the ketone. All right? So which is going to be preferential? Which is going to be preferential, do you think? Will this be preferential? Remember, these rings are sticking out. These are flat as a pancake. Okay? So let's have a look. This is the one possibility. Doesn't look too bad. There's space. But the other possibility, if it approaches the other way around, we're going to have the COOH group in the way of this phenyl group that's sticking out. To prove it to you, I'll try and build it. So we approach from the other direction. So the O is slightly tilted to coordinate. So you see, look at that. This COOH group here, in the bottom left quadrant, is clashing if it approaches from this face with this phenyl group. You see that? But if it approaches like this, the COOH group, which is the big group, is in this quadrant here, where we've got a flat phenyl ring, and they can they comfortably fit together. So it approaches from this face. It approaches from the Re face. And that's why we have a high stereochemistry in the system. And what is represented there is exactly what I've just shown you, using this quadrant argument, where the shaded quadrants are ones where there's steric congestion. And here are some other examples. So, you know, that's one example, RR dipamp. So R is the configuration of the one phosphine, R is the configuration of the other. But you have other possibilities. You can switch things around. You can have a situation like this, where the R configuration, you still have R configuration, so this is a different phosphine diop, but the quadrants are swapped around. So here you'd have those two quadrants shaded, yes?
I just have a question, because you said that you needed to have like a fixed geometry, but do you have it here though? Like,
Is there free rotation?
Yeah.
Is your question? The free rotation in principle is very difficult. Very difficult, because remember, the way that this is represented is with these nice long bonds, but if you look at a space-filling model, those things are already stuck together. But there would certainly be a higher possibility, if you will, of free rotation in this guy here than in this guy here, because here you've got this methoxy group that absolutely blocks any possibility of free rotation. But you can't, I mean, at a high temperature, possibly you might have some free rotation here, but there would be a high energy barrier associated with that.
And also, like, why do the methoxy groups anymore?
Good question. That probably has something to do with the fact that molecules like symmetry, because you see there's sort of a center of inversion here. Mm-hmm. Second point is maybe you have some sort of an interaction with the electron-rich benzene ring here, some sort of a pi interaction with a methyl group, right? Third possibility is it just so happens that energetically that's the lowest conformer. So the point is we can play around with the absolute stereochemistry at the phosphine groups. That's going to change using this quadrant arguments of Knowles the way that a prochiral is going to approach. And if it approaches in a certain way, remember, we have the approach, the preferred approach from one of the phases, and then what happens next? H2 activation. So now the hydrogen is going to activate in a concerted fashion, and you're going to get hydrogen transfer, and this carbon atom here is the one that's going to end up being chiral. And so depending on if it goes like this or like this, the H is either going to end up sticking this way or the other way, and you're going to end up affecting the stereochemistry. This carbon's not important because it's going to be achiral, right? You're going to end up with a CH3. This guy's going to end up being chiral after the hydrogenation. So that's how you can steer the stereochemistry formation, and that's sort of how it works. This is just again showing you the mechanism of an enamide. This is just a generic precursor for an amino acid type compound that you can steer the stereochemistry using these chiral phosphines. And here you see the hydrogenation in a cis configuration will necessarily determine the absolute stereochemistry of that carbon atom over there, which is chiral. Now there are other examples so that's work that was done by Knowles, and I just want to actually highlight some other examples of other contributions that have been made by Noyori. After all, he shared the Nobel Prize with Knowles and Sharpless, and he basically had the same idea, right? And he also built chiral phosphines. Now this, it's more difficult to see the chirality in that phosphine over there. Knowles' phosphines you can readily see are chiral because they've got different groups attached to the phosphorus atom. Now what Noyori did, which I think is genius, is he built phosphines where you have one sort of anthracene ring pointing up and the other one pointing down. And when that coordinates to a metal, it's locked in that configuration because there's a CC bridge here, and the whole thing is chiral, believe it or not. You can build a model and you can convince yourself. Now, the catalyst that he used, we call this ligand, by the way, binap, which comes from naphthalene, right? It's, again, following very similar arguments to what we've seen with Knowles. Enables one to, here we have again this prochiral alkene, to do asymmetric hydrogenation. And this is used industrially in the preparation of this anti-inflammatory reagent, naproxen. And we saw a moment ago, you might recall at the start of the lecture, the other stereoisomer is in fact causing liver disease. So, you know, it's important to get this right. And this catalyst does it very well. Now, I just want to make another announcement, and that is, it so happens that you can't always necessarily say that the stereochemistry or the absolute stereochemistry of the phosphine is going to be the absolute stereochemistry in the product. It just so happens in this case that they're both S, but you've got to really look carefully at the mechanism, and it's sometimes difficult to do that. Now, we've discussed CC hydrogenation, but there's also, of course, which is very important in natural product synthesis, asymmetric hydrogenation of ketones, which is also possible using, again, here we use basically the same, this is the same ligand system, or the same complex, Noyori, that in fact can hydrogenate asymmetrically this prochiral ketone. So this is a prochiral system. You can see the priority would be 1, 2, 3. So the top face is 1, 2, 3. It is anti-clockwise. So the top face is the C face. Bottom face is the side face. The bottom face is the read face. And if you take that, it turns out that you can get stereoselectively this isomer here, and that is a precursor for another medically important compound. So, very important stuff. This is the structure of levofloxacin, which is an antibiotic, a broadband antibiotic. this is the structure at the end. And you can see it's pretty simple to construct all of this here using classical organic chemistry. But to impart stereochemistry here in this position, there are techniques in organic chemistry that one can do that, starting with chiral auxiliaries and stuff like that. But you can, using asymmetric hydrogenation, basically build this precursor here, where you've built in the stereochemistry, you've built it in, and then retain that stereochemistry to the end, and end up selectively with one of the stereoisomers following the hydrogenation. And this is again just to show you some other medically compounds that are produced using asymmetric hydrogenation at some point in the synthesis of these compounds industrially. Ibuprofen, which is something we all take if we've had too much to drink and we have a hangover, right? It's good for headaches. And check it out. There it is. It's in fact got a chiral sensor, and that chiral sensor can actually be installed starting from a precursor which will have a CC double bond in that position. So exciting stuff. And this is just to end off today's lecture, a timeline of how rapidly this field developed. And it all started with good old Wilkinson, right, in the mid-1960s. And in the late 1960s and mid-1970s, that was when things really took off with the asymmetric synthesis of L-DOPA by Knowles and Monsanto. And people are continuously developing asymmetric systems to do these asymmetric reactions today. But the take-home message is, you need a prochiral substrate, prochirality, a substrate that in one step can be made chiral. You need a chiral catalyst. Not all chiral catalysts will work, but they must somehow, using this sort of these arguments we've looked at today, impart chirality in some way into dictating how the alkene coordinates. Now, we've seen this all before, haven't we? With the electron-alkene polymerization, right? Where the alkene, the propylene, coordinated in a certain way to a chiral system. In that case, it was group 4 metallocenes, and that dictated the tacticity of the polypropylene. And this is basically the same thing. You know, it all comes down to how do these substrates approach, and can you control the approach from which face these guys are going. And it's sometimes difficult